Warahmatullahi wabarakatuh and good morning. Okay, so today we will continue with chapter 1 part 1. So if you before we continue with the subchapter, if I'm not mistaken, in the lecture on Monday we stopped at subchapter 1.3.3. Okay, so today we will continue with subchapter 1.3.4. And before that, I would like to recap what you have learned on the last class, okay, last lecture. Okay, so if you still remember in the previous lecture on Monday, you have learned on the first one is the basic communication model. Okay, so you should know how to draw the communication system model, and you should know the function of each block. For example, what is the function of sender, modulator, transmitter, channel, receiver, demodulator, and also receiver. And you have learned on the simplex transmission mode. Okay, so you have 3 transmission mode, which are simplex, half duplex, and also full duplex. Okay, and you should know the difference and also the examples of this transmission mode. Okay, so what is the difference between half duplex system and full duplex system in terms of bandwidth, number of wires, and also signal channels. And then you have learned on the power measurement and also the unit that we will use in this subject, which are decibel, dBm, and also bell. Okay, and you have learned on basic calculation and how to convert from absolute power ratio into decibel, from decibel to absolute power ratio to dBm to absolute power, and vice versa. Okay, so in the previous example, you have learned on how to find the power ratio, okay, in the unit of decibel. So if you still remember your slide, okay, so this one, the slide on Monday stated here that this decibel unit is the most used unit, the most commonly used unit, okay, compared to dBm and also bell. And this decibel is used to define the power ratio between two signals. Okay, so this one actually we have you have done the example on how to calculate for the power ratio. Decibel also is used to express relative gain and losses in electronic device circuit, and also to describe relationship between signal and noise. Okay, this is number 1, 2, and 3. Okay, so this one describe the relationship between the signal and noise is the signal to noise ratio. Okay, or sometimes we call it as SNR in short. Okay, so SNR is signal to noise ratio. So in today's class, we will learn how we can express decibel to express the relative gain and losses in electronic device or circuit. Okay, so this one will be covered in subchapter 1.3.4. Okay, so this one. So if you look at this slide, stated over here, when a power levels are given in the unit watts and power gains are given as the absolute values. Okay, absolute values meaning no unit lah. Okay, the output power is determined by multiplying the input power with the power gains. Okay, so from this statement is actually stated that if, for example, you want to calculate for the output power, so output power I define as P out, PO. Okay, this is P out. So P out is equals to P input multiply with the power gains. Okay, multiply with the power gains. So power gain is AP. Okay. However, you must make sure that the unit, in order to use this formula, you must make sure that the power levels P in is in the unit watts. And the power gain is in the absolute values, meaning no unit. Then only you can use this formula. P out equals to P in multiplied with the power gain. If, for example, your P in is given in decibel, then you are required to convert from decibel to watt. First, then only you can use this formula. Okay, so now let's look at example.
Itu bukan, tak tahu lah.
Okay. Okay. So for example 6, given a 3-stage system comprised of 2 amplifiers and a filter, and given the input power P in is equals to 0.1 milliwatt, the absolute power gain you have 3, AP1 equals to 100, AP2 equals to 40, and AP3 is equals to 0.25. Okay, so to solve this kind of question, okay, so if no figure is given, okay, to make it easier for you to understand this statement, you can draw, okay, draw the system. So how to draw the system over here? So you can draw the block diagram. So you have a 3-stages system. So you will have 3 blocks, okay. So the first block here is the amplifier, because you have 2 amplifiers and a filter. So this is amplifier 1, this is amplifier 2, and this is the filter. Okay, and given the P in, so this is the input, this is the output. So P in is here. So P in is 0.1 milliwatt. P out, you don't know the value. And also the question also gives you the absolute power gain. So you have 3. So AP1 is the absolute power gain for amplifier 1. So AP1 is 100. AP2 is power gain for amplifier 2, which is 40. And AP3 is the amplifier gain for filter, okay, 0.25. So now the first question asks you to calculate the input power in dBm. Okay, so the input power. So given here, the question already gives you the input power, but it is in watts. Okay, so you need to convert this 0.1 milliwatt into dBm. So how to convert? This one actually you have learned in the last lecture. Okay, so you just use the formula for the dBm. Okay, so dBm, P in the unit dBm is equals to 10 log P divided by 0.001. Okay, so because it is the question asks you to calculate in the unit dBm, so you must divide with 1 milli. Okay, 0.001. So 10 log, your P is 0.1 milli, divide by 0.001. So you will get this should be negative 10. Okay, negative 10. If, for example, the question asks you to find the P in the unit decibel, so to calculate that, you must use the formula 10 log P. Okay, so just multiply with 10 log. We don't need to divide this with 0.001. Okay. So the next question, find the output power in watts and dBm. Okay. For P out here, calculate P out. Okay, so to calculate P out, you can use this formula. P in multiply with the power gain. But you must make sure that the P in is in watts, the gain is absolute values. Okay, and for this example, there is no problem because you already have the P in the unit watts, and also the power gain are all in absolute values. Okay, so you can just directly use the formula. Okay, so now let's calculate for this one. So for B, P out is equals to P in multiply with AP1 multiply with AP2 multiply with AP3. Okay, so P in use this value. Do not use the values in the question A. In A, you already calculate in dBm, so do not use the values of the input power in dBm. Use in watts. So 0.1 milli multiply with 100 multiply with 40 multiply with 0.25, you will get 0.1. Okay, so now the next question. Find the dB gain of each of the three stages. Okay, so over here you have three stages. You have three gains. Okay, but all the gains are in absolute values. The question asks you to convert the gains in the absolute value into decibel. Okay, so to convert absolute values into decibel, you can just multiply with 10 log. Okay, so see here. So the first one, AP1 in decibel is 10 log 100. So just use your calculator, you should get equals to 20 decibel. For AP2 dB, this is 10 log multiply with 40. Okay, it should equals to 16 dB. And the last one, AP3, 10 log 0.25. So you will get the answer is negative 6 dB. Okay, so now let's proceed to the last question. Find the overall gain in dB. The overall gain is actually the total gain. Okay, so you have three gains over here. You need to find the total gain. So I name this as APT, which is AP total. Okay, in decibel. In decibel. So to find the AP total, you can just directly add this value. Okay, because the question asks you to find the answer in decibel. So you just add this value AP1 plus AP2 plus AP3. So 20 plus 16 plus, don't forget you have a negative over here. So this should be negative 6. So the answer is 30 decibel. Okay, So this one you can directly add this value, because in question C you already find the value of each of the power gains in decibel. But if for example you don't have the question C, okay, and you want to find the overall gain in dB, okay, you can also use AP TDB is equals to, you can directly use these values, but you need to multiply with 10 log. Okay, so 10 log 100 multiply with 40 multiply with 0.25. So you should get the same value, 30 decibel. Okay, so you can use either one. Okay, and you should get the same value. So any question for example 6?
No.
Okay. Faham Okay, so now let's proceed to example 7.
Doktor nak tanya,
Yeah.
kalau ada point tu tak payah ambil
Point mana?
Dekat AP2 tu, jawapan dia 16.02 kan?
Yang mana?
Yang C tu,
C? Aha.
soalan C tu, AP2 tu,
Oh, point
jawapan dia 16.02 dB.
Boleh je letak, tak ada masalah.
Okey.
Okay, so next example 7. So example 7 is similar to example 6. Okay, still you have a 3 stages system given the P input and also you given the power gain. But the difference is you can see over here the P in here now is given in the unit dBm. Example 6, the P in is in the unit watts. And also the power gain in example 7 is given in the unit decibel. Okay, so the question asks you to find the output power. So remember, P out is equals to P in multiply with power gain. But you must make sure that this P in is in watts and the power gain is in absolute value. So you need to convert all of this P in, AP1, AP2 and AP3 into watts and absolute values. Okay, so first now let's convert P in watts into P in dBm, convert to watts. Okay, so this one is negative 20 is equals to 10 log P in divided by 0.001. Okay, so can anyone calculate for me P in? P in equals to?
Ten microwatt.
10 microwatt. Okay. Okay, so this one to calculate, okay, if step by step, this should be 10 to the power of negative 2 is equals to P in divided by 0.001. So you can calculate P in is equals to 10 to the power of 5. Okay. And next, you can convert AP1, AP2 and AP3. So this one dB into absolute values. So So this 13 dB is equals to 10 log AP1. So AP1 is equals to 10 to the power of 1.3. Okay, so you will get 19.95. For AP2, this is 16. So 16 dB is equals to 10 log AP2. So AP2 is 10 to the power of 1.6. So you will get 39.
39.81.
Okay, 39.81. And the last one, negative 6 dB is equals to 10 log AP3. So AP3 is equals to 10 to the power of negative 0.6. So you will get 0.25. Okay, so now then only you can use this formula. You can calculate for P out. So P in is 1 multiplied 10 to the power of 5 and negative 5 multiplied with AP1 is 19.95. I hope you can see this. Susah nak menulis ni. So multiply with 39.81 multiply with 0.25. Okay, so you will get the answer is
1.98 milli.
okay, 1.98 milli. 1.98 milliwatts. So this one is in the unit watts. This is in the unit watt. The question also asks you to calculate in the unit dBm. So multiply with 10 log P divided by 0.001. So P out in dBm ten log P, okay, 1.98 milli divided by 0.001. So you will get
3 dB.
ya 3 apa ulang balik
3 dB. dBm.
okay 3 dBm so make sure that the unit is correct. So this is 3 dBm. Okay, so the question here is quite simple. We just convert from absolute values to dB or dBm, then convert to watts and so on. But sometimes we change the question so that you get a little bit confused. Okay, so sometimes we can change. For example, we give you AP1 equals to 13 dB, AP2 equals to 16 without the dB absolute value. AP3 is negative 6 dB. Okay, so you must know which one to convert, which one you don't have to convert. Okay, kena betul-betul tengok betul-betul. Okay, so my question, based on this calculation, this system is having a power gain or power loss?
power
your
gain.
power gain. Why?
Because P output we got 3 dBm. In P input we have negative 20 dBm.
Okay. So you can directly see also. Okay, so from the value watts also you can directly see that the output here is bigger than the input. So you can directly know that the power is increased. Okay, there is a power gain in the system. Okay, so next,
Betul.
let's, yeah,
Power in berapa?
power in.
Power input. Nilai dia berapa? Negatif 5 ke negatif 3?
Ni jawapan dia.
Uh-uh.
Satu negatif, tanya negatif 5.
Negatif 5. Tapi saya kira dapat dekat power out dekat watt tu dapat 19 lebih.
19 lebih
19.86.
P out. Dalam watts ke? Yang mana? Sebab jawapan memang dah betul dah ni.
Oh betul dah. Okey tak apa saya silap.
Okay. So kalau salah pun is actually mana ni ya? This is 1.98 milliwatts. Tapi dekat saya actually I calculate 1.99. Okay, tapi dekat-dekat saya still terima sebenarnya. Okay. And you can also approximate this because I get the answer 1.99. I can also approximate it to 2 milliwatts. Okay.
Okay.
Okay, so next is subchapter 1.4. Okay, so for this one, if you still remember, lecture on Monday, we have learned on the communication system block diagram, and you have the modulator. Can someone give me the function of the modulator? What is the function of a modulator? To convert
signal.
To convert signal. Into
Channel yang untuk signal yang sesuai dengan channel.
Okay, correct. So the function of modulator is to convert the original signal or input signal into a signal that is suitable for the transmission channel. And I also already told you that the signal suitable for the transmission channel is the electromagnetic energy. This one, electromagnetic energy. So that's why stated here, communicating the information between two homologation is done by converting original information into electromagnetic energy. Okay, and then transmit to the receiver and then convert it back to the original signal. So from original signal convert to electromagnetic, that is the function of modulator. From electromagnetic energy convert to the original signal, that is the function of the demodulator. And this electromagnetic energy, it is the range is infinite. Okay, the range is very wide. Okay, infinite range consists of infinite range of frequencies, and this is given by this figure. So this figure actually shows you the electromagnetic frequency spectrum. Okay, so the frequency is the range is infinite. Okay, so from 10 to the power of 0 until 10 to the power of 22. Okay, actually it is infinite, and you can see that for different application it uses different frequency. So for example, you look at here for the radio frequency RF. Okay, so if I said RF, you should know that RF is radio frequency band. So radio frequency band, it varies from 10 to the power of 6 until 10 to the power of 12 Hertz. Okay, so this radio frequency band consists of AM radio, television, satellite and radar. All of this falls under the radio frequency band. We also have the optical fiber, okay, fiber optics. So for fiber optics band, it uses a higher frequency, okay, from 10 to the power of 12 until 10 to the power of 17. And also you can see that over here for X-rays, gamma rays, cosmic rays, it uses very, very high frequency. Okay. And now let's focus only on the radio frequency right now. We focus on radio frequency, RF. Okay, RF band. So RF band, it range from 30 Hz until 300 GHz. And this RF band can still be divided into a much narrower band. So if you look at here, these are all the application that falls under radio frequency band. Okay, so now let's look at the application that we usually use. For example, this one. Okay, so for television, mobile phone, radar, microwave system, we are using the ultra high frequency. Okay, UHF. This is ultra high frequency. The frequency is from 300 mega until 3 giga. Okay, and for microwave, satellite radio communication, it uses super high frequency. And you can see that over here for astronomy purposes. Okay, it uses an extremely high frequency which varies from 30 giga until 300 gigahertz. Okay, this is extremely high. And you can see that this is for astronomy, but for submarine, okay, underwater, you can see that we are using a very low frequency. Okay, terbalik So astronomy extremely high, submarine, underwater, we are using very low frequency where the frequency varies from 3 kilohertz until 30 kilohertz. Okay. And then the next, so when we deal with electromagnetic frequency spectrum, parameter that is very important that to deal with is the wavelength. Okay, so what is wavelength? Stated over here, wavelength is the length that one cycle of electromagnetic wave occupies in space. Okay, one cycle. And you can see that it is inversely proportional to the frequency of the wave and directly proportional to the velocity of propagation. This is the formula for wavelength. Wavelength is lambda equals to c divided by f. So c is the velocity of light. Okay, velocity of light, and this value is fixed. You need to remember this value. This is fixed, and f is the frequency lah. Okay, so from this formula, you can know that this wavelength is inversely proportional to the frequency, but is directly proportional to the velocity of light. Okay, so meaning over here, if the frequency is high, so the wavelength will be small. If the frequency is low, the wavelength will be wide. Okay. So if you look at this figure over here, this shows the electromagnetic wavelength spectrum. Okay. This one similar to the previous figure. This one. The difference is that this is in frequency, this is in wavelength. Okay, so you can see that dia terbalik. This one, cosmic rays, has a high frequency. Now, because we look into in terms of wavelength, you can see that the cosmic rays is having a smaller wavelength compared to radio waves. Okay, because wavelength is inversely proportional to the frequency. Okay, you can also see that from the figure, this one, this is frequency, this is wavelength. So if you look at here, so for gamma rays, it consists of high frequency. So you can see that, but for the wavelength, is very small. Okay, this one for radio, the frequency is small, but the wavelength is larger compared to gamma rays. Okay, so now, this figure, just to show you, for example, let's look at the first signal. This is the radio signal. Okay, this is the wavelength. This is 10 to the power of 3 meters. Okay, gamma ray, this is the wavelength, 10 to the power of negative 12. Okay, so the wavelength of radio is wider compared to gamma ray. The frequency of the radio smaller than the frequency of the gamma ray. So that's why you can see that this is the signal. Okay, this is low frequency, this is high frequency. Okay, and this is about the size of, you can see that gamma ray is about the size of an atomic nucleus. And in terms of temperature, you can see that gamma ray is emitting a higher temperature compared to radio wave. Okay, and from this figure also you can see that whether the signal can penetrate through Earth's atmosphere. So for example, for radio wave, it can penetrate to this one. Y is yes, N is no. Okay, so gamma ray, X-ray, ultraviolet cannot penetrate through the Earth's atmosphere. Okay, so this one, this figure is just for your extra information about the size, the temperature, and also the difference between the wavelength and the frequency for different signal. So now let's look at example 8. Calculate the wavelength. Okay, so this one is very simple. Directly use the formula lambda equals to C divided by F. This formula. But you must remember that the C is 3 multiplied with 10 to the power of 8. Okay, the velocity of light. So lambda 1, let's calculate for lambda 1. Velocity of light is 3, 10 to the power of 8 divided by 1 kilohertz. So you will get the value 300,000 meter. For lambda 2, this is 3, 10 to the power of 8 divided by 100k. So you will get 3,000 meter. For lambda 3, 3, 10 to the power of 8 divided by 10 mega, you will get 30 meter. Okay, so very straightforward calculation. So that one is for wavelength. Another parameter that is important is the bandwidth. Okay, so if you still remember, if you compare between half duplex system, half duplex with full duplex, you already know that full duplex is using a wider bandwidth compared to the half duplex. So what is bandwidth? Okay, so bandwidth is the difference between the highest and the lowest frequency contained in a signal. Okay, so for example, you have a signal ranges from 300 until 3000 hertz. Okay, so you have a signal range from 300 to 3000 hertz. So you want to find the bandwidth. So the bandwidth is the difference. So to calculate the difference, you need to minus the highest value minus the lowest frequency. Okay, so the highest frequency here is 3000 minus the lowest frequency, which is 300. So you will get 2700 Hertz, and this is the bandwidth. Okay, so over here is stated that a bandwidth of a communication channel is difference between the highest and the lowest frequency that the channel will allow to pass through. And the bandwidth of a communication channel must be equal or greater than the bandwidth of information. So you still remember your transmission channel. So for example, this is your transmission channel. Okay, so channel is like a path. Okay, jalan. A path to send the information. So stated over here, this is the bandwidth of the communication channel. So it stated that the bandwidth of the information, this is the information for example, the bandwidth of the information must be smaller or equal than the bandwidth of the communication channel. Okay, what happens if the bandwidth of the information is bigger than the channel? For example, this is the channel, and this is your bandwidth of the information. Okay, so if the bandwidth of the information is bigger, you can see that there will be a information losses over here. Okay, sebab jalan dia kecil, information banyak, besar. So there will be information loss. So this is what it means by this statement here. So example, a voice signal contains frequency 300 to 3000. For that, a voice signal communication channel must have a bandwidth of 2700 or greater. So this 2700 is the minimum. Okay, so this is the minimum value. If the communication channel bandwidth is greater than 2700, then lagi okay lah. Okay. And the final parameter is the information capacity. So information capacity is a measure of how much information can be propagated or transferred through a communication system. Okay, so berapa banyak information you can transfer. It can be expressed in the function of bandwidth and transmission time. Okay, this one. Okay, so over here is information capacity I is directly proportional to the bandwidth multiplied with transmission time. Okay. And this one, and in 1948, this person, Shannon, it comes out with what we call as the Shannon limit for information capacity. Okay, which is this formula. So based on the law, the information capacity of any communication channel is related to its bandwidth and the signal to noise ratio. So this is the bandwidth. This is the signal to noise ratio. Okay, so I hope that you know what is signal to noise ratio. Okay, so the higher the signal to noise ratio, the better the performance and the higher the information capacity. So if you look at here, signal to noise ratio is signal divided by noise. So for a good system, of course we want the noise to be small. So if you have a value here, you have a value here. Okay, and the value of the noise is small, so you will get the signal to noise ratio is bigger. So when you get a bigger value here at the signal to noise ratio, okay, so B log to 1 plus signal to noise ratio, you will get the bigger, higher information capacity. Okay, so this is what it means by this statement. Okay, so you can either use this law or this one, this formula, but usually we use this one. Why we use this one? Because if you look at here, this is log 10. Your calculator, if you use the log function here, this is log 10. Okay, so you can directly calculate 3.32 bandwidth log 1 plus signal to noise ratio. This one is log 2. Okay. Now let's look at example 9. So example 9, for a standard telephone circuit with a signal to noise ratio. Okay, signal to noise ratio. This is signal to noise ratio and a bandwidth of 2.7 kilohertz. This is the bandwidth. Determine the Shannon limit for information capacity. So this one directly use the formula I is equals to 3.32 bandwidth log 1 plus signal to noise ratio. So 3.32 bandwidth 2.7K log 1 plus, for the signal to noise ratio, you must make sure that you use the absolute value, 1000. Okay, even though in this question it already gives you the absolute value and also the value in dB. For this equation, you must use the absolute value, so 1000. Do not use this one. If you use 30, you will get the wrong answer. So this is 26.9 K. The units is bits per second. So BPS. So 26.9 kilobits per second. Okay, so for example, if the question only gives you 30 dB, then in order to calculate for the information capacity, you must make sure to convert this first into absolute value. Okay, so benda-benda ni yang penting. You should know when to convert, mana yang awak tak perlu convert. Okay, so any question for this week lecture? So no. Ahmed? So we have come to the end of chapter 1 part 1. To me, the chapter 1 part 1 is quite simple. Actually, to me, chapter 1 is quite simple. Okay, so next week we will continue with chapter 1 part 2. Okay, so I will upload the slide maybe this afternoon. And also I will upload the tutorial. So maybe you can try to do some of the tutorial. Okay, so next week we will continue with chapter 1 part 2. Okay. So if no question, then I think we can finish, we can end our class for today. Okay. So thank you very much.
Thank you.
Thank you, Doctor.
Thank you,
Thank you, Doctor.